исторически взятых, это тоже нет задачи, отражающих суть, но уже люди пользуются. Вот.
Okay, let's start. Today we have Professor Oleg Astafiev from neighboring lab of quantum artificial systems, who kindly agreed to accept our invitation to give a talk about his business, let's say.
Okay, my scientific work, I would say. Okay, thank you very much for inviting me here. It's a good opportunity to show what we are doing experimentally, and we are in 100 meters from here in the laboratory building. So, first of all, the title of the talk I've shown is Coherent Quantum Phase Slip Effect in Superconductors, but after thinking a little bit, I decided to change it and to make some kind of tutorial introduction into the superconducting quantum systems. Essential part of my talk will be related to superconducting quantum systems, and I will touch some physical aspects of coherent quantum phase slip in superconductors. Yes, and my affiliation is Skolkovo Institute of Science and Technology and Moscow Institute of Physics and Technology. And okay, honestly speaking, the second one is the main one. But I'm hired by 100% of Skolkovo. And we are kind of tightly collaborating, and the laboratory is in quantum superposition between two sites. So, first of all, recently it turned out that Nobel Prize was unexpectedly, I would say, awarded for macroscopic quantum mechanical tunneling and energy quantization in electric circuits, or electric circuit. And these two phenomena are related to two physical phenomena. The first one is quantum phase slip effect, and the second one, using the second one, someone can build so-called two-level quantum systems and use it for different applications. So it's obviously the work is relatively old, so it's done in middle of 90s, last century, and the work is so the Nobel Prize is definitely inspired by the boom in quantum computing. So far, no applications and no practical devices, but the boom is really, I mean, it attracts a lot of money, and probably it's okay. I should say that the work is really interesting and physically very important, but still the question is how it affects physics in general. We are working actually in both directions. And actually about macroscopic quantum tunneling, nobody usually says that it's a phase slip effect. Usually there is some, I mean, people present some analogy with alpha particle decay. But from the point of view of superconductors, it's a phase slip effect. And I will tell about this a little bit later. So, but first of all, let me make some introduction in our laboratory and what we're doing. The laboratory is rather big. It's not all members. It's difficult to collect all members simultaneously. Everyone busy with some, I mean, someone is busy with some unexpected things, but most of people are here. So the laboratory is funded in 2015 within top 100 project at the time when our rector of our university was the Minister of Education. So we have about 30 people. We're doing a series of research directions. I will not count them, and later I will tell you a little bit more in details. So we like physics, but need to do also some practical related to quantum computing. And I would like to ask, you can ask questions, and I even prefer to ask questions during the talk, then the talk becomes more productive. So the outline of my talk. First of all, I will make introduction into Josephson junction effect. Josephson effect. Will explain you what the Josephson junction is. We'll show you the first qubit realization quantum state control, which is the charge qubit, so-called. Then I will make some introduction into quantum mechanics of electrical circuits, and show you the directions of research of our group very briefly. And at the end, in the last part of my talk, I will tell you about the coherent quantum phase slip effect. So the talk is really heavily changed. And this I already told you that the Nobel Prize is inspired by the boom in quantum computing. It's definitely so. Okay. So, just to explain you what the Josephson junction and its property, I prepared this slide, and it's a little bit unusual way of presentation of the Josephson effect, but I wanted to make the analogy, to show the analogy between inductor made of superconductor. We will not consider any dissipation in our system, and the Josephson junction. First of all, if you have inductor, then the current flowing through the inductor is associated with the magnetic flux phi, and between the current and the magnetic flux there is a coefficient which is called inductance. It's actually just inductance couples the current and the magnetic flux. And the energy is phi square magnetic flux square divided by 2L. It's clear, everyone knows from textbooks from school. And let us introduce this new quantity. And this quantity is called superconducting phase, which is normalized magnetic flux by the flux quantum and multiplied by 2 pi. So it's number of magnetic fluxes multiplied by 2 pi in terms of magnetic flux quanta. And magnetic flux quanta is Planck constant divided by 2e. And formally it's equal to 2.0 by 10 to the power minus 15 Weber. It's a small quantity, but still detectable, and it's possible to do something with this. And now, using this quantity, let's rewrite this current, and current can be written in this way. We have some constant multiplied by this dimensionless parameter phase. And strictly speaking, to calculate the energy of superconductor, of this inductor, we integrate current multiplied by voltage. And here I need to say that voltage doesn't exist in DC current. Everyone knows about that. But in dynamics, voltage voltage appears, and it can exist during change of some parameters, for example, current. And using this, so we integrate this power, and eventually we got this energy, which is actually equivalent to this. But here we introduce this inductive energy. So sorry, it's a mistake here. No, it's not a mistake. So this inductive energy is presented in this way using this quantity of the current I introduced here. And now, if we take superconductor and make some small gap, the current in the system still can flow because of overlap of wave functions. And it's not visible here. It can be moved.
Assumptions made.
Oh, okay, that's fine. That's fine. Yeah, the current in the system can be written in this way. It's some constant, which some constant multiplied by sine phi, sine of superconducting phase. This relationship can be obtained using some simple calculations with considering the tunneling of particles or current through the tunnel junction through some barrier. But anyway, so let's just take as it is. So the current is proportional to sine phi. And now we can calculate energy of the system in the same way as we calculated here. It's this integral, and as a result, we have this equation. So the energy is proportional to some constant multiplied by 1 minus cosine phi. And if we draw these two plots, we will have the inductance, energy of inductance as a function of phase or magnetic flux. It's parabola, and this equation actually shows cosine, and these two equations coincide with each other when phi is smaller than 2 pi or pi.
Where is the characteristic of the isolator? So some properties of the isolator should be.
It's inside of this quantity.
But this classical doesn't have the, I mean, left side doesn't have this property. Why do
No.
it coincide?
No, okay. But again, if you calculate, sorry. So ATPS and the current, when you calculate the tunneling current through the barrier, so ATPS in the current, and the property of barrier will be there.
Yeah.
So it will be, so you calculate the tunneling, and the tunneling probability will enter this quantity.
Yeah, but here they coincide near the phi equals 0.
Yes. And the point is that it doesn't mean that I take exactly same inductance. No inductance here. I just break it, and of course, we need to tune parameters to make. Oops, what is this?
Never mind.
We need to tune parameters of these two systems to make the coincidence of these two. So it's not straightforward. But anyway, so important consequence that this tunnel junction behaves as an inductance when phi is small. And also this circuit can be redrawn in this way. So to denote the tunnel junction in superconductors, people use cross, and the equivalent of the circuit is shown here. And again, in dynamics, voltage appears. So now, if we take again this inductance and add capacitance, we'll have LC resonator. Everyone knows this, and the frequency of this resonator is 1 over square root of LC. And let's introduce additional quantity. This we already introduced. It's same as introduced on the previous slide, but rewritten in a bit different way. I didn't use phi naught here, but use explicit expression for this via charge and the Planck constant. And let's introduce additional quantity, so-called charge and energy, which is Q square over C. Usually people use a little bit different notation. Actually, there are several notations, but typically for single particle, I use Q0 square. Q0 square is charge quantum divided by 2C. In a single electron transistors, for example, people using electrons for this, but in our case, Q0 is 2e because the elementary charge in superconductors is two electrons, a pair of electrons. They form so-called CQPS, but I think this is well known for everyone. So now, if we introduce these two quantities, we can calculate so-called plasma energy, which is square root of product of these two. And we can make some simple calculations and find that the energy is h bar over square root of LC. This is trivial. And what we have this parabolic potential and energy levels inside of this potential equally spaced energy levels. So in this splitting is resonant frequency of the resonator, and we can call it plasma energy. Now, if we consider again Josephson junction and this circuit and add the capacitor, then we will have a similar situation. We will have almost parabolic potential here and equally spaced levels. But because this potential is not parabolic, then the energy levels becomes not equally spaced, and it's clear that there is a deviation of behavior of this system. If this plasma energy is close to in value to the Josephson energy. But now I want to come back to the experiment of the Nobel Prize winners, and they worked again 40 years ago, yes, and they worked with very large Josephson junction, which is 10 by 10 micrometers, and this is a really big system. I mean, it's of course small for human eye, but in reality, it's really it's a big system comparing to the systems people are using nowadays. Sorry. So they didn't have the technique to make smaller one at that time. And critical current for this system, it was 30 microamperes, which can be recalculated in the Josephson energy. And to denote the energy, it's convenient to use frequency. So the energy divided by Planck constant. And in values, this is this value. This big junction means, okay, here schematically drawn this. So we have two metals and insulator between them. And because of big size of this, you can see that this is parallel plate capacitor. And yes, please.
Is the spacing too large? So you see the length of a group pair is just several tens nanometer or 100 nanometer.
First of all, this is of course very schematic representation, and just to have your idea of what it is. But the distance between two metals, typically in the Josephson junctions, typically nanometers, say 2 nanometers. So it's more or less typical. And this is very schematic representation, just to give you, you see that this is 10 microns, but this is 100 nanometers. It's not in scale at all. Right, and we can calculate the capacitor of this. It's approximately this. I just made these calculations, and the plasma energy is 2 to 10 to the power 10. It's 20 gigahertz. It's a frequency of microwave range, and the technique is well developed in this range. There are some commercial generators which can be used for the experiments with this frequency. And what's important here that EJ over this quantity over this quantity is 10 to the power 3. So what does it mean? It means that this is 10,000 times smaller than this. And if we draw, then we should draw this potential, which will be more than 1 meter high. This is, yeah, and there are many levels. So it's a very good harmonic oscillator because it doesn't feel any unharmonicity. And of course, if people measure this, if they apply microwave, they will see just excitation of this resonator. But still, there is a trick to observe, to make the system nonlinear. So, but the goal of this experiment was to make the system nonlinear. So we take this circuit and we add here the current circuit. current source, and the bias this junction is the current source. So we apply current. And application of current actually changes this diagram, this energy diagram, to this one. So it becomes tilted, so-called washboard potential. I didn't tell you that this potential is called washboard, because you know that in former time people used it to wash their clothes. Okay, and now what it means? It means that if the particle, okay, no, let me just later I will explain you the exact meaning of this. But anyway, just believe me that this circuit is described by this tilted, so-called tilted washboard potential. And now you see that if we really heavily tilt this potential, then we can leave several levels inside of this structure, inside of this potential, and at some point it becomes anharmonic. And now, because we also decrease this barrier, and at some point again, the probability of tunneling of particles, say from this level, becomes finite. So tunneling of this particle, it's so-called phase slip process. It means that actually phase. So what we have jumping of particle from this to this point, and with this actually didn't show you here, but this scale is in phase, and this is 0, this is 2 pi, this is 4 pi, and etc. And tunneling particle from here to here means that the phase changes by 2 pi. And this change of particle, of phase by 2 pi is actually accompanied by another physical process, which means actually tunneling of flux quantum. So one flux quantum tunnels from here to here, in this case.
Maybe may I ask something?
Yeah,
at
two
this
questions
point?
simultaneously. Yes, yes, please.
So it's of course a very general question. When you say particle, what do you mean by particle?
Okay,
here?
so I mean the following. Actually, here we have, of course, electrical circuit, you see, but the physics is exactly same as physics of a real particle in the parabolic potential. So instead of this, I will actually use this analogy later to explain you what it is. But in principle, we can consider instead of this electrical circuit, just particles sitting inside of harmonic potential. And then people use this terminology to explain the behavior of electrical circuit, in particular Josephson junctions. So using the word particle. So in principle, we can, if we prepare this type of potential in real space, and we use some small particle, I don't know, electron, proton, or whichever, then we will have exactly the same physics, tunneling, and etc. So,
and what defines the effective mass of this
okay,
particle?
I will answer this question later, because I will come and will show precisely the answer on your question.
Thank you.
Okay?
Yes.
Yeah, my question was about phase slip. So if a particle tunnels through one barrier here, so it can tunnel.
Sure, that's what I wanted to say just after this. Yes, precisely. If it tunnels once, then it will continue going further, and the critical current just disappeared, voltage appeared in the circuit, and that's it. It starts working in in dissipative regime. Yes, precisely. So we will have in. I will come back to the previous slide. Oh, sorry. Here. So I didn't tell you. So in principle, we can measure IV characteristics in this circuit, and below this IC has meaning of so-called critical current. And again, the physics I showed you, it actually takes place just close to this. And here we have so-called supercurrent, the current without any voltage in DC regime. Right, and here is dissipative regime. So what's happened after this process of tunneling, then the system jumps to this dissipative regime. There is a voltage and some probably bigger current and stuff. So we just go away from this superconducting regime. Okay. Yes. Okay, so and in this work, people, so these people, oh sorry, not this shown. They don't. They are not shown here. The Nobel Prize winners, they demonstrated nonlinear behavior. This I can again come to the to the first slide, and they observed actually different transition frequencies here. So they apply microwave, and then particles are tunneled, and they observed the so-called switching currents, and found that there are several transitions in the system, and the frequency is different depending on the level you.
Surprisingly, if you say that they are in the regime of quasi-classics, so how they could see resonances, some resonances, because they would be smart, because there are a lot of levels.
All right, but again, that's for this case. But now what's happened that it's tilted, so this goes down. And then they tilted it very close to the critical current. It means that, okay, this is very schematic also. It means that this barrier becomes really very small. And so that there are only few levels here, not only the thousands. They heavily change the potential, heavily disturbed. Yes, please.
May I ask a very naive question?
Yes, please.
So this picture arises from periodicity of the phase, distinguishability of states different by more than 2 pi,
Yes.
2 pi periodicity. But it actually doesn't account, so one could actually give the physical meaning to phase difference more than 2 pi by accounting for an integer number of phase windings of 2 pi's, and that would contribute some energy. So
no, here actually no difference between these states. This state, this state, these states. In fact, this is this picture. I mean, people who are deeply in this field, they say that this picture is not correct because we should draw just only single.
like the state.
Yes, precisely. And this is, of course, some tricky thing. I drawn this keeping in mind several things. For example, I keep in mind again this physical process which is accompanied by the phase slip. So going from here to here, actually accompanied by tunneling of one flux quantum. And later on, I will come to. I will explain you a little bit deeper what's going on physically. Okay.
But you have discrete spectrum here because it corresponds in this periodic potential. Discrete spectrum because not zone spectrum, because the periodic.
That's also a good question. I didn't show you formation of zone, but strictly speaking, it will appear. And I just want don't of course, yes. I don't want to make to add some complications at this stage. Later on, I will tell you about this. But the case is, I mean, when the Josephson energy is large, when the barrier is large, yes, and tunneling is suppressed, Josephson energy, yes, then they become very, I mean, the energy bands, yes, the levels becomes thin, and then you can forget about the bands. Yeah, but yeah, thank you. It's a good and deep question. Right, and now, in fact, we can say that in that time, in 85, people already demonstrated a quantum system, and in principle, they could make a superconducting qubit based on that, but they didn't think in this way at that time. And probably experimentally, it was still not very easy to do. And the first qubit realized was first superconducting qubit, the first two-level system, I would say, was realized not in this type of system, but in so-called superconducting Josephson charge qubit. And here I just want to make introductions and explain you how it works. First of all, let's take a superconducting island. It can be even a sphere somewhere in the universe, far away from any metallic surfaces. But I explicitly introduced here some metal and capacitance between the island and the reservoir. So that's a huge metal, probably ground. And now what we have, the energy of the system is just charge square on this island divided by 2c. C is the capacitance of this island. And we know that the charge is quantized here, and in superconducting case, we can add or remove charge quantum, which is 2e. Again, I call it Q0. And then the charge allowed in this island can be n multiplied by Q0. What it means? It means that the energy of this island is n Q0 divided by 2c. And I already introduced this quantity, but now I introduced in more general, more classical ways, Q square 0 over 2c. And then the system has this type of energy levels, which is charge and energy multiplied by number of charges in the island. And then we can draw these levels. So this is, and consider them, and can go to quantum mechanics and call it 0 state. This is 1 state, this is 2 state, this is 3 state. The only problem that, and also one additional requirement, of course, experimentally, that this energy must be larger than thermal fluctuations, just to ideally 0 temperature. So we have quantum system. The only problem is that we can do nothing with the system because we cannot manipulate the number of particles here. But anyway, so let's do something else, and let's add here voltage source coupled to this island via some small capacitance. Or let's call it CG, which means C gate. This is additional gate. And then the energy of the system, so the potential of the system can be changed by varying this voltage, and it's continuously changed. And in fact, the energy of the system now can be rewritten from this expression to this expression. We add some additional small number n, which is continuous and associated with the potential. So Vg can be continuous, and therefore this is integer, and this is continuous number or continuous value. And now, if we have, for example, 0 state, so here we have this energy states 0, 1, 2. So 0, 1, 2 is somewhere here, 3 is somewhere here. And now we change this gate potential, and we can change the energy of 0 state. If we add one CQPS pair here, so then the 1 state goes in this way, 2 state, state 2 goes in this way, this is 3 state, etc. So what we have again quantum system, but now we even can control the energy of the system and go to some point where, for example, there is a degeneracy between 0 and 1 state here. 0 and 1 state are degenerate, as it's shown. This happened when n small is equal to 1/2. So controllable quantum system without possibility to really control it, because no way to add or to remove charges. So what it means that if we are staying in 0 state and we are changing now gate voltage, we will continue going this up along the 0 state, but there is no coupling between 0 and 1 state, so this is isolated. We assume that it's isolated and the charges, no source of charges. Or if it's 1 state, then we go along this parabola, also going to any energy without changing this. This is non-equilibrium state, but still no source of particles. And to add the possibility to change the number of particles, we add here tunnel junctions. Essentially, Josephson junction is already shown. And in that case, what's happened is that if the system was in a degeneracy state 0 and 1, then this degeneracy is lifted, and the splitting between these two states is the tunneling energy. And tunneling energy is the Josephson energy in our case, in case of superconductor. So when we have actually, instead in this degeneracy point, instead of two degenerated states 0 and 1, we have state 0 plus 1 and 0 minus 1 over square root of 2, of course.
But there are other degeneracies.
Of course,
Why?
yes, of course.
Why they're not splitting?
They're splitted, all of them are splitted. Look, what we do, we apply this gate voltage so that to bring system to this point. There is
No, I mean higher.
Yeah, so there is, but it's a second order process and etc. So it's if this splitting, I mean, if this energy, if the charge energy is large, then this energy difference is large, and therefore this splitting will be small. But it's also important, and I will also mention this effect later. Yes, of course, there is a splitting.
I think.
Yes, please.
I think that the higher splittings are in the second order of perturbation.
Yes, that's what I told you.
Because
Yes.
they are kind of angular momentum difference of 2 or something like that.
Yes, precisely. Tunneling energy EG square over 2 energy differences between these two states. Yeah, I just do not. I just don't want to talk about this at the moment. Later I will show you this. Okay, so such kind of quantum systems was realized later, and I will show you. But now I want to tell you a little bit about the how to treat these systems. So we had this plot, and then we added Josephson engine. The plot becomes like that. And by the way, what we can do now, we can change this potential and move slowly, for example, along this ground state. And in this case, what's happened is that the system was with 0 number of particles. Or maybe I will return back to the previous slide. Oh, sorry. It was with 0 number of particles somewhere here. Then, okay, 0 doesn't mean really 0, but it's a neutral position. It's a number of positive charges is equal to number of negative charges at this point. And then, if we change this voltage slowly, then we're sitting in the ground state. We had 0 number of particles. Then this is superposed state. Then 1 particle, 2 particles here, and etc. What's happened is by changing this voltage, the CQPS tunnel 1 by 1 to the islands. So we have possibility to control the states in this way as well. Okay, next. Next, we have this energy diagram, and we can now write the Hamiltonian of our system, which will consist of 2 parts. First of all, the electrostatic energy of our system. So this I've already shown you, and the state will be, I mean, yes, it's NN state, and we have additional exchange term, tunneling particles between neighboring state n and n minus 1 and minus 1n, and we can write this in terms of matrices. So we have this diagonal as electrostatic energy, and shifted by 1 from the diagonal terms present the coupling between neighboring states. For example, this is 1, 2, this is 0, 1, and this is, oh sorry, 1 minus 1 minus 2, minus 1 0 0 1 1 2. And now, if we look here, this actually part of this total Hamiltonian. Okay, let me tell you the following. So in principle, we can we should write the Hamiltonian in this way. It's charge operator square divided by 2 capacitances, and here we have this tunneling, which is EJ cosine phi, where phi is also operator. And this part corresponds to this, and this part corresponds to this term. And in matrix form, it looks like that. And now we're interested in this 2-level system. So if our charge energy is large, then these levels are sitting somewhere far away. and we can consider this two-level approximation good enough to describe our system. So now we take this and make it symmetric a little bit. So we made the energy just in between these two levels. And then this part of the Hamiltonian describing two neighboring states only can be rewritten in this symmetric form, where epsilon is the difference between this and this. And so in matrix form, it becomes like that. And using Pauli matrices, it can be rewritten in this simple form. So this diagonal part and off diagonal describing Josephson part or tunneling between two neighboring states. So, as I told you, this was the first quantum bit demonstration. In 1999, it was published in Nature. And actually, I came a little bit later. I came to this group in 2001, I think, and stayed there for something like 12 or 13 years. So in total, I spent 16 years in Japan. Anyway, so the experiment looks like that. Probably I will not go in all details, but just show you some important thing. So it was fabricated using some special lithography technique, but I will also show you a little bit later. So there is an island. Okay, maybe better to look here. So we have some metallic aluminum island made from aluminum. And it's connected to some reservoir. Here we have reservoir and two Josephson junctions. It can be even single Josephson junction, but due to some reasons, I will not go into details, and they used so-called sweet geometry. So island connected to the reservoir via the tunnel junction. And they have also additional junction just to read out the system. And now, so this is the central island, these two Josephson junction, this is the Prof junction, this one. So, and they did the manipulation in the following way. So here I redrawn just two states, split it by the tunneling energy, and they put the gate voltage somewhere here. This is the gate voltage, and here this voltage source, so somewhere here. So we start from this point where this ground state is 0, and then apply non-adiabatic, actually rectangular pulse, bringing system to this point. And here, as I already told you, there are two eigenstates, 0 + 1 and 0 - 1. So 0 state is actually decoupled into these two, and each one evolves with its own factor defined by the Josephson engine. And there is an oscillation if we consider the probability to be system in 0 and 1. You will see that they oscillate like in a harmonic way between 0 and 1. And then what they do, they terminate this pulse and return back to here and see the projections to one state. If a system in one state, they have one extra Cooper pair, and then repeating these pulses, they have some current, which in maximum is just proportional, to the pulse rate multiplied by 2e. So, and experimentally, as a function of the pulse, duration of the pulse, they observe such kind of oscillations. So in these oscillations, they demonstrate that it's possible to control the quantum states, particularly. So here they had state 1, somewhere 0, but they cannot make infinitely small pulse. It was a limitation in the pulse length. But anyway, starting from here, from 0, they go to 1, then again to 0, to 1, and somewhere in between, the state is superposed, and they can make superposed state in controllable way. And people realize that now they can control the quantum states and do some interesting experiments. And this was done by these people, Nakamura, Pashkin, Sai, and published in 1999.
But these oscillations seem to be relaxing.
Sure, of course. Yeah, that's always a question and a problem. And, once you are working with this quantum system, there is a finite relaxation time, dephasing time, whichever. I mean, you are working like in optics, but the way of manipulation here is a little bit different. So now it's a time to explain the system, to introduce the quantum mechanics of the systems in general, systems based on Josephson junctions. In principle, to do that, you can take you can write Lagrangian of the systems, then introduce the canonical variables, and then introduce these quantum mechanical things. But I use here the easy way just to show, and also more informative way just to show the analogy. The question was already related to that, between the mechanical system and electrical system. First of all, mechanical system, you have this classical momentum, which is mass multiplied by speed. And you have, first you have position and speed, which is x dot, the derivative of the position by time. And the momentum is mass multiplied by the velocity, and kinetic energy mass multiplied by velocity square over 2. And then using this approach, I told you, you can introduce these quantum mechanical operators, and particularly it's known that the particle momentum is just derivative d over dx minus I multiplied by h bar. So now we can consider, instead of particle with mass m, we can consider the inductance. And then what we have charge, and the charge motion, which is q dot, is the current. And then we can introduce also this quantity, the magnetic flux. I already introduced this, but anyway, the magnetic flux is inductance multiplied by current. And here there is a mistake. It's not minus, of course. Sorry. And then it can be written this way, and you can see the full analogy of this. And then the kinetic energy is inductance multiplied by q dot square over 2, and the current square over 2. So there is a full analogy of this, and in this case, inductance has the meaning of mass in this approach. And then again, we can similarly to this introduce this quantum mechanics and introduce a momentum operator, which is magnetic flux operator, and now it's derivative d over dq. And then here it was the commutation relation of this kind of xp equal to I h bar, and here if you introduce this q and phi operators, then the commutation relationships will look like that. And then answering the question was at the beginning. So q has a meaning here in this approach. Q has a meaning of position, phi is momentum, and inductance is mass. Okay, it works, but there is another way.
You just impose this commutation relation to have energy levels. Am I right in our So
you can use quantum mechanics to calculate the energy. So calculate quantum mechanical systems and eigenstates and energy levels. Yeah, but no. Sure. Once you have quantum mechanics, you can describe your system quantum mechanically.
Excuse me, please. May I ask the question?
Yes, please.
Concerning the very left and the central pictures. You see, the coordinate in quantum mechanics is continuous quantity. Charge Q is discrete. So, what is the to which extent it is reasonable to have this analogy between quantized charge and continuous variable x?
So yes and no. In principle, no. First of all, if you are talking about physical charges, yes, they are quantized. and magnetic flux is also quantized, but it depends. Yeah, that's a good question. I need to think a little bit, but it depends on what system you're considering. In principle, there can be for example, magnetic flux can be not quantized. So to quantize magnetic fluxes, you need loop. But maybe better to go to the next slides, and I will show you where you can consider the one of these quantities not quantized.
Can I ask one more question?
Yes, please.
I see the current expression is I equals to dq over dt, but then we use it is phi, and phi is equal to minus L.
No, I told you that it's mistake.
It is a mistake.
It's mistake, yes.
And
So that's plus.
The right-hand side is also a mistake.
No, that's correct. Q voltage is minus. Okay, but let me
But
come.
the error in the expression for the voltage.
Let me come to the. I didn't tell you anything about the right. Let me first explain this, and then you will ask a question. Okay. So now, but you can use another approach. You can consider magnetic flux as a coordinate and introduce a voltage which is phi dot, which is derivative. Okay, sorry. This minus should be put here. Sorry, it was intermediate slide somewhere, and then okay. So this is minus, right? This minus voltage is minus phi dot. And then we can introduce charge, which is C multiplied by voltage. And then we substitute in magnetic flux instead of voltage, we will have this Q, which is equal minus C multiplied by phi dot. And then we can introduce this kinetic energy. And that's also possible to use this approach. And then the charge operator is becoming the derivative by phi. And commutation relationships becomes this kind of. And then in this case, we have phi instead of x, q instead of p, and c instead of mass. So in this approach, mass is capacitance. And you can use any of these approaches to describe your electrical circuit. But usually people using Josephson junctions and dependence on phase, they prefer to use this approach because then it's not needed to take derivative from or to do something with potential. The Josephson potential becomes just potential. Okay?
Can I
Yes.
maybe a question or a comment? So about the previous question, apparent contradiction that the charge is quantized, but actually it depends on how we define the charge. If we define it as the number of charged particles in the particular area, then it's quantized. But if we allow these particles to be delocalized, it can be.
Yes. That's a correct question. That's what I meant actually. I mean to explain you. So to observe the quantization, you need really to localize. When I said about the loop, it means that you indeed can localize, and the particles will be quantized. It's a matter of definition. Yeah, that's a good answer. Right. And what was the question about this? Right.
Now it's okay.
Okay, let's move further. So now there is some small summary of two different types of qubits. By the way, time is almost over.
Yes. But we can, if we extend.
Okay, I will move faster. So in principle, we have two approaches. I told you, two extreme cases. The quantized charges in the island, and we can take a loop, and then we will have quantized fluxes in the loop. And in this case, we have energy of this kind of, in this case of this kind of, but these two equations are symmetric. And now, so the general circuit for the qubit is shown here. So you can actually use some different variations of the circuit, but so basically 90% of superconducting qubits is described by this circuit. In this case, inductance is infinite or zero, or not zero, sorry, it's just open circuit here. In this case, inductance is finite. And this without inductance, it's a charge qubit, but with inductance, it's another extreme case. It's so-called flux qubits. And now you can play with this potential, with Josephson potential. It can be cosine. I already explained you. You can add inductance. There is an inductive part, so you have sum of these two. And in this case, the potential becomes more complicated. It's cosine sitting in the parabola. And you can realize different potentials and different types of qubits working with different principles. So now I told you about the charge qubits, but charge qubits I demonstrated you are not really used anymore nowadays, because they are very much sensitive to charge noise in the substrate, and charge noise is usually large. But what people do, they usually use, again, same circuit, but large capacitance. So this I already shown you. So you have we have energies with some splitting here, and splitting here is even not visible. But now if we increase capacitance, we decrease charging energy, so-called, and this parabola becomes less and less steep. And here you see this ground state behaves in this way, but then with smaller, larger charging energy, with larger capacitance and smaller charging energy, it becomes flatter. And here this splitting appears, which you asked. So here it's not visible, but now it's appeared. And then with further increasing of capacitance has become, so this energy bands becomes flat, but these are still oscillating. And we are eventually coming to the case I already shown you this Josephson potential and energies. But now we have this broadening in the energy bands because of finite probability of tunneling of particles between the wells. So it's
could you please explain? So the difference between capacitance and induction, it is just in the width or this dielectric layer between two superconducting contacts, or there is any other difference?
The difference is here the difference is just regime. The regime is now different. The capacitance is large, and therefore charging energy is small. That's it. I mean, we need to compare these two energies. If I answer your question, I didn't really.
Yes. So basically, it is quantitative. So the real device that is capacitance, it is the same Josephson junction, but very large.
No. The real devices are shown here, and Josephson junctions are small. Here you see on the right-hand side, this is a Josephson junction, which is small, 100 by 100 nanometers, roughly speaking. But here you have large capacitance. These metallic areas, they are capacitances. So the capacitance is different. Is additional. It's added. There is some small capacitance with the Josephson junction, but there is some external capacitance, which just presented here as a big area of any shape.
Okay.
So now it's like that. Okay, and let me a little bit continue about this width of this. And width of this is just basically this maximal and minimal energies. Okay, and people like to suppress, of course, this broadening, these bands, to work with them with quantum circuits with as narrow as possible lines. But this problem of bands broadening is solved if you add inductance. And inductance, I already told you, this part actually makes potential very much different because we added the parabola. And then this problem of Benz formation disappears because there is no periodic structure anymore. And some of this flux, so-called flux qubits. So, okay, this type of qubits called flux qubits, or sometimes RF qubits with essentially one Josephson junction for which tunneling happened. So if these Josephson junctions are large, then they're working as an inductor. But the small, particles prefer to tunnel via this small junction. So instead of inductance, people use series of Josephson junctions, which are working in linear regime, and then we have this type of potential. So if we apply external magnetic flux, we move cosine function, and then at some points where we apply half flux quantum, we have this barrier and the formation of these two levels. Okay, splitting of levels because of finite tunneling energy. And this, for example, system can be also treated as a three-level system. We can again work in the limit of two levels, but in principle, we can consider this as a three-level atom and demonstrate some quantum optics with three-level atom, which is also classical objects of quantum optics. So, and this is a spectroscopy picture, and there is another example of RF squid or flux type of qubit, two Josephson junctions and some inductance between them. So we can play with these Josephson junctions and inductances to form different type of potentials you like. Okay, and now to make the experiments, we use the following facilities. So this field is actually requires a lot of things. For example, nanotechnology to make small junctions, say 100 nanometer size structure. And also we need low temperatures to work with the systems. We need to cool down to millikelvin range. And then we need this microwave technique to apply for frequencies to excite the system and to control the state. So all this is required, and all this costs a lot. And now it's a subject of sanctions. So to get this equipment nowadays is not easy. But by the way, China is actually working hard to avoid the sanctions because Russia is under sanctions, it's clear, but China is also not allowed to buy essentially this equipment, this and this and this. But there are, for example, 10 lithography. No, but I recently heard that China developed a lithography system just very recently, and it is Christoph as well. But there are, I know personally, 10 startups approximately developing refrigerators. And now I heard that the lithography system is also developed. Okay, the time is really short, and I will move further. So there are several directions of research in our group. We're doing quantum optics. Some fancy pictures are shown here. We're doing quantum acoustics. This part, which is supposed to be the essential part of my talk, but now I will very briefly touch this. And quantum computation, of course. Honestly speaking, I don't like this. I like all these physical approaches, but we have to do this because money are coming for funding are coming for quantum computing. Okay, so just several words about quantum optics. So we can, because our system is quantized and it's well controllable, we can consider our systems as our system as an artificial atom. We can put it, we can fabricate it on top of chip, of substrate, and make some transmission line, one-dimensional transmission line, and put some microwave here, and then this quantum system will interact with the microwave. It's very similar to quantum optics, but the difference is that we're working with one-dimensional channel. But there is no essential difference in physical phenomena we observe. So we can make different things. For example, this single photon source on demand with very high efficiency, 99%. It's a dream of people working in optics. We can make spectroscopy of our systems, put it in open space. I had a paper published in Science in 2010, I think, which opened this direction, open quantum systems with superconducting artificial atoms. This is resonance fluorescence. You can see 3 peaks here, but again, I will not go into details here, and then because
Create quantum states with the light.
quantum states.
Squeezed, for example.
Yes. That's more. That's well established. It's not really a problem at all.
And can you reach strong coupling region?
Sure, we are reaching a strong, physically strong coupling regime where for example, we prepare some excited states, and then the photons emitted to the line with probability of more than 90%, comparing to some non-radiative relaxations, for example. And also, if we consider the resonator here, resonator is shown, then we have splitting. We observe 2 peaks and splitting directly, which is also not trivial in optics at all. Yes, so we can do many things. Quantum computing. Can I skip it?
Yes.
No, if I have time, I would say several words, but
Could you say some? It's interesting.
we are working with but I'm not going to go deeply anyway. So we're working in these projects building quantum processors in Russian. It's called Дорожная карта, but I don't know even how to translate it. Roadmap. Sorry, yeah, of course it's trivial. Roadmap. Right, and we're developing quantum processors with different number of qubits. At the moment, we have 40 qubit quantum processor.
So each qubit is a single junction.
Each qubit actually here they're shown. This is capacitance and some small Josephson junctions which are not visible, and we can control the states in each qubit, and they interacting with each other. I will not go into details, otherwise it will take a long time. And we are trying to demonstrate something practical. Of course, not advantages, not supremacy, not advantage, but just some quantum algorithms. And we are moving in the direction of quantum machine learning. And surprisingly, we can do several things. For example, we can distinguish handwritten numbers with high probability of, digits from 0 to 9. So we demonstrated this recently. Surprisingly, this working. And now the last part, we shall spend probably 5 minutes for that, very briefly. So I will talk about the quantum phase slip, which is again this process I already mentioned. So now probably this slide is the most important slide. So when I told you about the Josephson effect, I told you that we have 2 superconductors separated by insulating gap, small gap, so that the wave functions are overlapped. In this case, we can observe a CQPS tunneling between these 2 and supercurrent in these systems. Now, if we swap space and superconductor, we will have 2 insulating spaces and superconducting wire separating 2 insulators. And now we can consider tunneling of magnetic vortices, especially, so we can take a loop here, can quantize the vortices if you like, and apply a magnetic field, and they will tunnel to the right side. So here we have Josephson energy, and we can introduce additional quantity, which is called phase slip energy, where we have VC, it's critical voltage. I will show you on the next slide what it is, instead of critical current. And here we use duality, actually. Here we considered tunneling of charges, but here tunneling of vortices. And each tunneling of vortex is actually accompanied by flip of phase by 2 pi. But physically, again, it's tunneling of magnetic vortices. So experimentally, people dream to show this coherent quantum tunneling of vortices in superconducting systems. Unfortunately, in usual wise, it doesn't work, but recently people are using so-called highly dissolved superconductors, which are different from classical superconductors in the sense that if you create a vortex, then the core of this vortex is not dissipative. So it's very much different from traditional abricosal vortices, where the core is formed by normal states, right? And motion is associated with dissipation. This inductance is separated from the outside world by this meandering-like structure. It's made of same material. Material is niobium nitride, very high kinetic inductance. So this very narrow, about 10 or 20 nanometer wire separated from outside world by very high inductance is about 10 microhenry, which is really huge number, but they are very compact. It's also essential part of the experiment. And in first glance, we observed again the behavior like superconductor, some vertical line in IV characteristics with some current, which or apparent critical current, looks like critical current. But if we look attentively to this part, we observed some blockade. And the blockade is actually, that's what we aim to find. Actually, we, in case of Josephson junction, we observe the current without voltage, but here we should observe voltage without current. And in principle, we have blockade, which is signature of transport of vortices without current. And then the critical voltage is this one where this stops working. Now, if we apply microwave, we observe steps similar to Shapiro steps, but in current domain. So each step corresponds to 2e multiplied by frequency. So you see different frequencies, and in DI characteristics, we observe some Bessel-like behavior at each step, the first step, second step.
Sorry, can I ask you a very fast, very simple question?
Yes.
It is numerical simulations, and the numerical simulations include noise, yes? Do you have something
Yes.
like noise?
Okay. That includes some, yes, some dissipation, yes.
So dissipation or noise?
I think noise actually done by yes, I know it's different includes.
Okay.
Includes. Noise is dissipation, actually similar things. I don't know, I don't remember exactly what he added, but of course he added some realistic parameters. I'm just afraid to tell something wrong. But it's, I mean, without any dissipation, without noise, you would observe usual Bessel functions, but they are decaying Bessel functions. Okay, and yes, probably I'll skip this. And so we use some different approach to this, but I will probably, maybe this plot is important. So this is the compilation of many experiments. What we have here, we have position of the step as a function of frequency, and the middle of step actually is, okay, there is a one-to-one correspondence between frequency and current, and they're sitting on the line. And if we, right, they're sitting on the line, and here the deviation of these experimental points from this line is shown. So it's within some small range. And we already can define the charge I'll copy pair with the accuracy of 1,000, third order of accuracy, 3.2, 0 plus minus 0.01, 10 minus 19. So I cannot go into, the very last slide. I cannot go into details, but I will tell you why it's important. So there is a so-called electrical metrological triangle, which includes three quantities: voltage, so one version of this triangle, voltage, resistance, and current. So these two exist as quantum metrological standards. This is Josephson, AC Josephson effect, Shapiro steps. This is quantum Hall, quantization of resistance. And this one doesn't exist so far. And now with this new result, it can be achieved eventually. And then we will close this metrological triangle, and each quantity can be verified separately. So that's an important ingredient in the metrology. And one more thing, the metrology now, in metrology, recently scientists redefined the metrological constants. They are fundamental physical constants. So before that, the standards, metrological standards, were not related directly to fundamental constants, but now they are related. So that's it, and I will leave you for my conclusion. So, okay, thank you very much, and sorry for the delay.
Questions? Do we have questions in Zoom?
Maybe I would ask one more, if you allow me. These, let's say, artificial atoms, obviously they can be described using similar quantum mechanics to what we use for real atoms or real electrons. The question is, what about the measurement? Because we know that when we measure a superposition state of an electron, we project its state to the classical basis and we find it either, I don't know, in state spin up or in state spin down. But if it would be a classical particle, we could find it in any state in between. So here, this is a many-body object. So when you do the measurement, is it the real quantum measurement that collapses the wave function of this object, or it is kind of something different?
This is the main point, actually. The objects are indeed macroscopic. And for the experiments I've shown you of these Nobel Prize winners, they use 10 to the power 12 atoms. But still, it behaves as a quantum object. And now probably strictly speaking, these objects even larger. But still, they behave quantum mechanically. And in our measurements, with these quantum computers, for example, we see very, very well the quantum mechanical behavior. For example, if we have superposed states, so we can prepare superposed states in our quantum bit, and then we can make projective measurements. We do it. And after making the projective measurements, we have either 0 or 1. If we do not do, and we continue manipulation, it behaves like 0 plus 1. But these projective measurements work purely as in quantum mechanics textbooks explained. So we just see it. And for students, it's very, very, I would say, useful probably to see how quantum mechanics works. And we have very good access to it.
Thank you.
No question.
Can we say that duality between charge and phase, charge and magnetic flux is just reflects the property between charge and vortex duality?
I didn't understand the question, because charge and magnetic flux and charge and vortex, vortex is charge, vortex is a magnetic flux.
I mean the charge vortex duality in the context of XY model, for instance.
Charge vortex, I don't know what model you mean.
Okay.
Well, maybe we can discuss later. Probably it makes sense, but I just didn't understand it.
An alternative maybe just reflects the coordinate momentum duality.
Yes,
So it's another way to
but that's what I've shown you.
No, it's
Sure, suppose the IDV curve that you should you use BCL function to simulate the Y BCL, so it will result after solving the quantum mechanic problem.
Say again, the beginning, I missed some.
I want to see the IDV curve.
The IDV curve, okay, yes. Mhm.
Right.
basic function.
Statement is they have place for asymptotics.
Yes. Mhm.
Why BCL doesn't copy the
Why it's Bessel?
just
Because it's cosine from cosine. It's like in Shapiro steps. Like in Shapiro steps, yes. We modulate the argument of cosine or sine. So the current is sine of phase, and phase is modulated harmonically. Then sine from sine.
A question with Sam, I was and there's no sign of the cost center.
Okay, thank you. Because, да, что-то я увлекся. Замечать должен тот, кто рассказывает.
Про ту картинку, которую вы показывали, там где